Although computers were originally developed to deal mainly with numbers, it quickly became obvious that representing text, including letters and punctuation, was just as important. Many of the applications we write need to be able to represent and store text. In fact, imagine how a C++ compiler works. It reads in a program, written in text, and converts it to machine instructions. The compiler itself has to be able to process text. We've been using text for output in many of our cout statements already. We've seen ways of putting text in double quotes and then streaming that text to the console, like in the text we output for random numbers in our random number example. The term for text like that, a collection of letters, numbers, punctuation, spaces, etc., all grouped together, is called a string. It's called a string because you can think of it as a bunch of individual characters all strung together. Up to now, we've been using only string literals. When we say literal, we mean a specific fixed value of some type. Think of a literal as being in contrast to a variable. A variable has an identifier, its name, and can potentially be any value of a certain type. On the other hand, a literal is some specific value. If we have a variable x and a line of code like x gets 5, the x is a variable, while 5 is a literal. If we stream 3.14 to cout, we're streaming a literal floating point value. Or, if we assign 3.14 to a floating point variable f, then when we print f, we're streaming a variable. Just like we can have variables to let us store and manipulate numbers or Boolean values, we would like to have variables to let us store and manipulate strings. To do this, we're going to introduce a new type of variable, the string type. String variables are the main way that we process and manipulate text data. Now, I should mention at this point that the idea of strings was around even in C. But C++ offers a much richer way of dealing with strings. So we're going to focus on the C++ way of handling strings, since it's generally much easier to use. Now, unlike int, float, and bool, a string is not a built-in language type. To have access to a string type, we're going to bring in a new library, the string library. Once we've done that, we can declare string variables, just like we declared other variable types. The string library is one of the standard C++ libraries, so to have access to it, we simply #include string. And everything in string falls in the standard namespace, so using namespace standard at the beginning means we don't have to list the namespace explicitly. This example program is a different variation on the Hello World program. Since we've #included string, we can declare variables to be of type string. In this example, we've declared a variable of type string, named greeting. We then assign greeting a value, which in this case is the string hello world. And finally, we output greeting, streaming the value of our string to cout, just like we would have streamed out a string literal. When we run the program, we see hello world printed out, just like we did in the original version. We can stream input into a string, just like we streamed a string to output. That is, we can use cin to get input from the console, and stream that input into a string variable. The code we have here is a simple greeting program. Like our previous program, we #include the string library. And we declare a variable of type string, which we name username. After prompting for the user's name by printing the text, "What's your name?" we then read the user's response into the string variable username. The syntax is just like streaming other variable inputs, cin, greater than signs, username, semicolon. We can then stream the string as part of an output statement, so that we can say howdy back to the user, using the user's own name. Let's look at what happens when we run this code. If I run it and type in John, I get the message, howdy John. That's just what I'd hoped for. On the other hand, if I type in my full name, John Kaiser, I still get the same response. Howdy, John. I don't get a howdy, John Kaiser. But we know that strings can contain spaces. We've seen that in many of our string literals. So why didn't we get the full name stored in the string variable here? When we stream input into a string, the stream will just take the next individual item entered and put that item's data into the variable. Individual items are considered to be the text elements separated by white space. That is, spaces, tabs, or line breaks. So, when I typed in John Kaiser, the streaming operation saw that as two different strings, one with the value John and one with the value Kaiser. Only the first string John got streamed into the variable. Here's a different variation on the program, one designed to handle both first and last names. We have two string variables declared, first name and last name. We also adjust our prompt to ask for both first and last names. Then, we stream into both variables, to both first name and last name. This means that the first string entered will go into the first variable, first name, and the next string entered will go into the second variable, last name. The output statement is also changed. Notice that in streaming the output, we have to explicitly output a space between the first name and last name, otherwise they would run together. Now, when we run the program, if I enter my name, John Kaiser, I get the complete greeting, howdy John Kaiser, back from the computer. Let's practice this for a minute. Let's say that we want to write a program that asks a user for their name and their favorite color, and reads that information in. Then a reply is printed telling the person that the computer likes that color too, using both the person's name and favorite color in the output. How might you program this? Well, here's one way you might have written that program. We begin with our standard structure to begin the program, but also adding #include string to the #include IO stream and using namespace standard and int main lines. Remember that these import the IO stream and the string libraries. And note that we're using the standard namespace, and then we identify the point at which we're starting the main part of our code. We need two string variables, one for the name and one for the favorite color. So we declare those as string username, comma, favorite color, semicolon. Next, we prompt the user and read in both the name and favorite color. To read in the strings, we have a cin command, with the input flowing to each of the variables. And finally, we output a response, in which we stream both username and favorite color to the output. Running the program, if I type in John when it asks my name, and blue when it asks my favorite color, I'll get a message back saying, John, I like the color blue too. On the other hand, if I type in John Kaiser, it'll use John for my name and Kaiser for the color. Okay, so we can stream in data with cin. But what if we want to read in a longer piece of text, like a sentence with spaces and all? Remember that we can look up what's in the string library through online references like c++.com. There's a function defined within the string library that'll let us read a longer section of text. And that function is called getLine. To use getLine, we make a function call. Do you remember how we do that? Right, we use the function name followed by parentheses. It looks like a function in math, so that's easy to remember. The parentheses will contain the arguments to the function. For getLine, we'll want to use two arguments. The first argument will be the source of the input. For now, we've only seen one source of input, and that's the console input cin. The second argument is going to be the identifier of the variable that we want to hold the result of the function call. And this should be a variable of type string. let's look at how we could modify our Hello World program to use getLine. In the code you see here, all the commands are identical to the ones we saw before, except the input command. Rather than streaming from cin to username, we're instead using the getLine function. We just write getLine, open parenthesis, cin, comma, username, close parenthesis, and semicolon. That command will read in an entire line of input into the string username. Now if we run this program and enter John Kaiser as the name, the output will include the entire name, writing, "Howdy, John Kaiser." So, let's review. How would you declare a string named favorite food? That would be string favorite food semicolon. Remember that you should have pound included string and had using namespace standard at the beginning. Okay, how would you then assign a value, pizza, to that variable? You'd write favorite food equals, quote, pizza, quote, semicolon. How about if you wanted to stream in the string from input? That would be cin double greater than favorite food. What if we instead wanted to read in an entire line? We'd need to write getLine, parenthesis, cin, comma, favorite food, parenthesis. And finally, what about streaming to output? Well, that's cout double less than favorite food. Now, let's look at a few operations that we can perform on strings. Take a look at this code. We have 3 strings named S1, S2, and S3. And we assign the string happy to S1 and the string birthday to S2. Then we have a line S3 gets S1 plus S2. That is, we're adding together 2 strings to get a third string. Any guess as to what happens here? Well, if we run this program, we see that outputting S3 gave us a string, happy birthday, with no space between the words. Basically, the string S3 was formed by taking the first string happy and sticking the next string birthday right onto the end. The term for this is concatenation. We have concatenated the strings S1 and S2 to form S3. Notice what this means. It means that the addition operation, plus, works differently for 2 strings than it does for 2 numbers. We say that the plus operator is overloaded, so that it takes more than one meaning, depending on the types of input. Operator overloading is a common practice for defining behavior between different types. Later on, we're going to learn to make our own types and overload operators ourselves. But for now, we just want to realize a plus sign does not always mean addition. The meaning of various operators will vary depending on the type of the thing that they're operating on. In fact, subtraction, multiplication, and division have not been defined for strings. If we try to subtract one string from another, that hasn't been defined, so we get an error. Let's look at another variation on the previous program. Now, instead of the strings happy and birthday, we assign S1 the string 3 and S2 the string 4. What do you think happens when we add these 2 together? In this case, the result looks like 34. Why is that? Well, keep in mind that S1 and S2 are strings. The 3 that's assigned to S1 is not the number 3, it is a string that so happens to have just a single character digit, the digit 3, inside of it. And likewise, S2 is assigned the string 4. And when we add together strings, we get concatenation. So the result of adding S1 and S2 is to concatenate their strings. So the result is not really the number 34, it's the string 34. Let's look at another operation that I think you can figure out yourself. In this code, we have a string S that we initialize to the value happy. We then have a line s plus equals the string birthday. Based on what we know, what do you expect will be output when we run this? We'll get a concatenated string, happy birthday, with no space in between. The string birthday has been appended on to the original string, which was happy. Basically, we took the value already in the string, and we performed a plus operation with the right-hand side, putting the result back in the original variable. But plus for strings is defined as concatenation. So, the two strings were concatenated together, and the result placed back in S. So, when a variable is a string, the plus equals operation is the same as append, since we just append the new string onto the end of the existing one. Now, there are some unexpected effects of adding strings that we can run into. Take a look at this code. We have a string s, and we try to assign s the sum of two string literals, happy and birthday. You would probably expect that adding together happy and birthday like this would be fine, and we'd just get a concatenated string. But that's not the case. Instead, we get a compiler error, basically telling us that we're not allowed to add the two string literals together. For general purposes, an easy rule of thumb to remember is that we're not allowed to add together string literals. We can add together string variables, or we can add a string variable and a string literal, but we cannot add two string literals. A string is basically made up of an array, or a vector of characters. A character is a letter or digit or punctuation or space, etc. And a character has its own built-in type. You don't need to pound include any libraries to have access to it. The type is the char, which is pronounced either char or char. Either way is okay. I usually say char. To understand how this works, remember that C already had a form of string that it could use, but C++ improved things with the string class. This is nearly identical to the situation that we described with arrays and vectors. In C, a string was basically an array. In C++, although there is still an array under the hood, the way we use a string has many more vector-like options. Here's a very basic program using a char-type variable. Notice that we didn't need to pound include any special libraries to use the char. We just have iostream so that we can output to the console. We can declare a variable named testchar of type char just by writing char testchar semicolon. We can then assign a value to testchar, in this case assigning the letter A. When testchar is streamed to output, we see an A printed to the screen. Now, notice that for a single character, we enclose that character in single quotation marks. That's the same as the apostrophe key. In C and C++, characters are enclosed in single quotes, and there can be just one character inside. Strings, remember, use double quotation marks, the standard quotation mark. Now, one slight word of caution. The single and double quotes should be the basic standard quote mark. If you use a word processor, it will often help by changing these to curly quotes that go one direction or the other. These curly quotes are not the same thing, and they'll cause errors in your program. So be careful if you ever use a word processor to write your code. As for what can be stored in a char variable, it can take on any of the standard characters that we would type. These are called the ASCII characters, and each character you can get on a keyboard, letters, numbers, punctuation, spaces, and so on, is assigned a number. The first 32 numbers are control characters, followed by 92 printable characters, starting with punctuation marks and then numbers, then letters, uppercase, then lowercase. In fact, if we assign a number to a char variable, we're meaning that it will have the corresponding ASCII value. In the example here, we assign the number 66 to the char variable testchar. When we output it, we see the character in position 66 in the ASCII table, which happens to be capital B. I want to quickly mention a few special characters that end up being very useful. The first one is the new line character. This is a character that means end the line and go to the next one. You know how we've been streaming endl to end a line of output? Well, that's actually printing a new line character. We can write the new line character in a string directly, but obviously we can't hit enter on our keyboard. That would just end the line of code, rather than put a new line in the output. The way to write new line is as \n. We can put a new line character into a string of text. Then, when we run the code, we get a new line at that point in the text. Notice that even though you actually have to type two characters, a \, and an n, this is considered just one single character in terms of how it's stored in memory. It's the ASCII character number 10. There are other special characters as well, which we have to use a \, to designate. The \, is called an escape character, and it means that the next character will indicate what special action to take. \n is a new line, as we saw. \t is a tab. \0 is what's called the null character. To get a quotation mark, we need to write \quote if it's part of a string literal. If we don't, it will look like we're ending the string instead of trying to write a quotation mark as part of the string. To get an individual character that's a single quote, in other words, an apostrophe character, we use \apostrophe. Now, this only matters if it's a char literal, where we have just a single character, since otherwise the apostrophe would look like we were ending the char. And how do you think we get a \, itself? Well, a \, itself actually needs to be represented as two \. Typing just one would look like an escape character. There are some others also, but those are the most commonly needed special characters. Now, in C++, a string is basically a vector made up of chars. That's different from the way strings were handled in C. C basically used an array of chars, with an extra null character, the ASCII 0, at the end to mark the end of the string. Even in C++, a string literal is still treated like a C-style string. And since we can't add arrays, that's why we couldn't add string literals. In both C and C++ strings, a particular character in a string can be accessed by using the square brackets. And since C++ strings operate like vectors, they have all the nice features that vectors had over arrays. The @member function, for example, to access a particular character and ensure that you don't go out of bounds in the array. Here's an example. We declare a string s, and we initialize it to the text, "This string is not a not." If we output s sub 0, that should give us the first character in the string. Remember that indexing starts with 0. The first character is a capital T. If we output s at position 3, that will give us s sub 3, which is the fourth character in the string. In this case, that's a lowercase s. We also have the ability to get the size of a string, just like we got the size of a vector. For strings, it's easier to think in terms of length of a string rather than size, so a length command is also provided. This program takes a string s, initialized to "this string is not a not," and it prints out the size and length. Remember that we can use the length to loop through a vector, so in this case, we can use it to know how long to loop through a string. That is, it calls the member function size and the member function length, neither of which takes any arguments. That's s.size parentheses or s.length parentheses. In both cases, the result is the same, 27 in this case. Strings can be compared to each other as well. We can check whether two strings are equal. Checking whether two strings are equal means that every character has to be checked to see if it matches. And it's the same for not equal. Comparing less than or greater than is a little trickier. What they really mean is that we consider the ASCII characters and whether they come before or after. To compare whether one string comes before another string according to the ASCII table, the comparison will go through character by character to find the first character that doesn't match. If the ASCII value of the first non-matching character is greater in one string, then that string is the greater string. Take a look at this code. This code will let a user enter two strings and compare them letter by letter until it finds two letters that are not the same and see which letter is greater than the other. There are two strings declared, S1 and S2. And for each of them, we ask the user to enter a string, and we stream in the results from Cin. Next, we compare the results. If S1 is greater than S2, then we output that S1 is greater than S2. Otherwise, we output that it's not greater. Notice in the output that we're trying to output quotation marks. To do this, we have to use the escape characters we talked about before, writing \quote every time we want a quotation mark. If we run the program, we can test out various cases. Comparing strings like this is the basis for doing things like sorting in alphabetical order. Let's say that we want to compare a capital T with a lowercase t. Well, since the capital T comes before lowercase t in the ASCII table, then capital T is not greater than lowercase t. If we compare two strings that start with capital T and lowercase t, we'll see the same thing. The word test starting with a capital T is not greater than the word test starting with a lowercase letter. Just to verify that things are working, we can check the other way around. Sure enough, lowercase test is in fact greater than uppercase test. Now, what about comparing apple, all in lowercase, with zebra, starting with uppercase? Which do you think is the larger string? Well, what does the ASCII table say? All the uppercase letters come before all the lowercase letters in the ASCII table. So apple with a lowercase a has its first letter coming later than zebra with a capital Z. So apple will be the string that comes later, that is, the greater string in this example. Now, generally, you can use string comparisons to compare alphabetical ordering. So apple comes before ball, and aardvark comes before apple. You just have to be careful about things like making sure that you realize uppercase letters always come first, like capital Z zebra coming before lowercase a apple, and realize that punctuation counts when comparing, which can also throw off the ordering that you expect. Strings have a few other member functions that are useful. You can see a full list at c++.com. One of these is the function empty. This function returns a Boolean value that is true if and only if the string is empty, that is, it does not contain any characters. We'd write such a string as just two quotation marks, or like we saw earlier, as the C-style string that contained just the null character. In the example here, we declare a string variable news today and initialize it to the empty string. Then we use the member function empty to determine if it's empty, and if so, we print out a statement. In this case, it is empty, so the statement, no news is good news, is printed. Another function is the find function. The find function takes another string as an argument. It returns the position where that other string first occurs in the given string. Here we have two strings. The first one being S1, this is a test string, and the second one being S2, test. When we use the find function to look for string S2 inside of string S1, we see that string 2 occurs at position number 10. Remember, that means that it's at the 11th character. Be careful though. If the string you're looking for does not occur in the main string at all, then you'll get an answer that seems like nonsense. The value returned from find is actually a special value, defined as string : npos. That's the value that's returned if the string is not found. So, in this example, if we look for the string apple inside the string "this is a test string," we won't find it. The occurrence that will be returned is a crazy looking value that happens to be the one defined as npos. The way this would actually be used in typical code is to first check to see if the result is equal to that special value. If it's not equal, you can use the location that find returned. In this code, we have that comparison. If s1.find of s2 does not equal string : npos, and then we either print out the position or we print that the string does not appear. Let's look at one more function, the substring function, abbreviated as substr. Substring will take in two arguments, the first being the starting position and the second being the length. It returns a new string that is a piece of the old one. It will be the piece that starts at the starting position and is of whatever length is specified. In the code here, we have a string s1 defined to be the text, "This string is not a knot." Then another string s2 is the substring of s1 starting at position 7 and 4 long. Position 7 is the R in string, and so taking 4 characters from string s1 starting at that point gives us the new string ring. There are other member functions available for strings. For example, there's one named replace that lets you replace part of a string with another string. But the member functions that we've covered are some of the most useful for strings. Strings are very useful for processing and manipulating text data. It's common to read in text information, and we have both the getLine and stream operators to do so. And once we have a string, it can be useful to manipulate it, to compare for alphabetizing, or to find where it contains some special word we're looking for. The tools we've seen here will help us do all of that, letting you treat texts as data in all sorts of programs. Our next lesson will talk about different ways that we can stream data in. We'll see how we can get data not just from the console, but also from files. And, in fact, we'll see how we can stream data from the strings we've just been learning about. See you then.